Okay. So this Box-Cox transformation is used to try to make our data look more normal, okay, more like a normal distribution. This is a family of transformation that's used in many cases. It's used in regression, and it's also used in time series analysis. The approach is different in regression, and the approach we're going to see here is to try to approach normality. So it's to try to transform our data so that the transformed data looks more like a normal distribution. Whereas in time series, the main objective of the Box-Cox transformation is to stabilize the variance. So the approach is different. The family of transformations is the same, but since the approach is different, the method to get the right value of lambda, which is the parameter that determines what transformation we're going to do, is slightly different. For our case here, and this is the same case in regression analysis, the approach is to maximize the likelihood function, to find the lambda that maximizes the likelihood function. Now that's a lambda for the univariate case, and in the multivariate case, we need to select one lambda for each of the variables, okay? And so in the multivariate case, the vector of lambdas that we are seeking is a vector such that maximizes the log likelihood of our different distributions for y1, y2, up to yp, for the p variables that we have, okay? So here S sub L is the variance covariance matrix of the transformed observations. So this is essentially the transformation. We'll be using it when required, when we need to transform the data so that it looks more normal. For a lot of the classification methods, when you have some of the predictive factors that have very skewed distribution, it's worth transforming them to have a distribution that's closer to a normal distribution. But we'll talk about those in particular when we require to discuss those things in the different methods we're going to be studying. Okay, so the next thing, I started talking about this thing a little bit, but that's I decided to leave it for today because it's important to understand this concept. When we talk about confidence intervals, every software that you use for any type of multivariate analysis will give you individual confidence intervals. Okay, let's suppose you're estimating a mean vector. It'll give you the confidence intervals for each of the means of the p variables. And if you want to do hypothesis tests, well, it'll also give you an individual test. But those two things are not equivalent to a joint distribution function or a joint hypothesis test. Okay, and to illustrate that, let's look at this picture here. We have a picture that shows the distribution, the joint distribution of two random variables. And we can assume that these are normal distributions. That's okay. And we are making inferences about the mean vector of the two random variables. If we only looked, if we look only at the, for example, confidence intervals, individual confidence intervals, the individual confidence intervals will not be giving you what the joint confidence region gives. And there's a couple of examples here. If and remember, there's an association between confidence intervals and confidence regions in the multivariate case and hypothesis testing. Okay, suppose that we're testing the hypothesis that mu, the first element, mu1 is equal to mu null 1 versus alternative, but it's different. And mu2 is equal to mu null 2 versus alternative that it's different. We're testing that hypothesis. That's equivalent to, since we have two-sided alternatives, it's equivalent to doing a test of, it's equivalent to building a confidence interval, okay? So now you can see here in this picture, if this is the actual value, this is the value of mu given the null hypothesis. Okay, that's the value of mu given the null hypothesis. And if this is the y, the vector of means, sample means that we obtain, okay, if we were to use a joint region to test this hypothesis based on the joint distribution of the two variables, then we would reject, in this case, at the significance level, whatever, 5% significance level, then we would reject the null hypothesis given this value of y bar, because this value of y bar falls outside the confidence region. Okay, it's falling outside the confidence region, so that's we would reject the null hypothesis. However, if we were to use only individual confidence intervals, this is this one here is the vertical. This one represents the confidence interval for the second bar for y2, let's say, and this is the confidence interval for y1. So as you can see, the y bar falls within the individual confidence intervals. So if we were only to use the individual confidence intervals, then we would not reject the hypothesis that mu is equal to mu null. Whereas if we use the appropriate confidence region, then we would definitely reject the hypothesis that mu is equal to mu null. Is this picture clear enough to illustrate the difference between doing a univariate tests versus doing a joint test for the different variables?
Yes, teacher, is clear.
Okay, because it's easier to see in 2 dimensions, but that extends to p dimensions. Now, yes.
Can you explain it again, please?
Yeah, sure. See, if I were to compute, we essentially have 2 random variables, right? Y1 and Y2 that have a joint distribution. They are jointly distributed. Okay, let's call that let's call the joint PDF f of x of y1 and y2. Okay, I have now. If I want to test the hypothesis that the mu1 is equal to mu01 versus the alternative, but it's different, I can just build a confidence interval for y1 and see if the mean falls outside that confidence interval. Then that means that I reject the null hypothesis. If it's inside the interval, then I cannot reject the null hypothesis. And the same thing for y2, for the second variable, I can test independent of y1. I can do a test to see if y2, if the mean of y2 is mu2 versus the alternative that it is not equal to mu2. And I can do that hypothesis test just building a confidence interval. If I'm testing at 5% significance level, I would build a 95% confidence interval. And if y2, the y bar 2 falls outside the interval, I would reject the null hypothesis that y2 has mean mu2, and against the alternative that it's different. Whereas if it lies within the confidence interval, I could not reject that null hypothesis. Okay, so here we have a case. This is the vector of mu. This is the vector that represents the mu1. So this is mu1 0, mu2 0. The mu01. I used it even order here. This is mu01, mu02. That's the mean vector under the null hypothesis. And this y bar here is y bar 1, 0, 1, y bar 1, y bar 2. Okay. That's my vector of observed means. If I were to use individual intervals to test these two hypotheses, then we would not reject the null hypothesis that the mean vector is mu null. Okay, I would not reject the null hypothesis that the mean of y bar one, the mean of y1 is mu 0, 1, and the mean of y2 is mu 0, 2. Okay. I would not reject them because y bar is within this confidence intervals. This here, from here to here, is the confidence interval for y2, confidence interval for mu 2. And this one here, the horizontal one, will be the confidence interval. This is the confidence interval for y1 or mu1. Okay. Now, if I compute if instead I use the joint distribution of x and y of y1 and y2, then this region is the region that represents the 95% confidence region for that mean. Okay. And if given that region, since y bar falls outside the region, then I would reject the null hypothesis that mu1 equals to that the mean vector is equal to mu null. Okay. So in other words, if you look at this in here, let me see what I did. No, okay. Essentially, what I'm saying is with individual intervals, in this particular example where I have my mean vector, observed vector here, then in this case, I would not reject H null. And for this case, I would not reject H null for this particular hypothesis. Now, if I want to test the hypothesis that mu1 equal mu1, mu2 equal as a vector to mu 0, 1 and mu 0, 2, using the joint region, we would reject H null, the null hypothesis. Okay. Did that help clarify the concepts?
Yes, teacher, thank you.
Okay. Now consider that this joint density function f of x1, x2, and that's given by 1/2 x1 plus 3/2 x2, and that's for x1, x2 between 0 and 1. Okay, and it's 0 otherwise. Did you download your notes from last class for this presentation or not? Anybody did?
Also,
Huh?
teacher, do you refer that we download the presentation?
Yeah, the presentation, yeah.
Yeah, I downloaded it.
Yes, me too.
Yes, we all did.
Then let's forget about this exercise because I forgot to put this square here to block the answer. That was going to be an exercise and I forgot to remove it. Okay, so instead of doing it an exercise, since you already downloaded this thing, you compute the marginals. The marginals for x1 you integrate over x2. Okay, and that's the integral of 1/2 x1 plus 3/2 of x2, but I'm integrating only with respect to x2, so that's 1/2 of x1 plus 3/4. Okay, when you evaluate this as 0 and 1. And the marginal for x2 is equal to 3/2 of x2 plus 1/4. So our X and Y, X1 and X2 independent. These are the conditional distributions of X2 given X1 and X1 given X2. So are X1 and X2 independent or not? Any votes for yes or any votes for no?
No,
No, right?
They are not independent. Why?
they're not independent.
Why aren't they independent?
Because if they were independent, the conditional distributions will be the same as the marginal distributions, right?
Yeah, that's correct. The conditional distributions will be the same as the marginal. So these are not independent.
Yep.
Now there is a distribution which is called Hoteling's t-square, and that is an extension of the t-test for the multivariate case. It's computed. Remember the t-statistic in one dimension. It's the mean minus the mean under the null hypothesis divided by the sample variance, right? It's the same thing here, except that we do not have this. The variance is a variance covariance matrix, so this is going to be n times, and now have vectors y bar minus mu null times s, the variance covariance matrix inverse, the inverse of the variance covariance matrix, and y bar minus mu. That's the extension of the Hoteling's. This is the Hoteling's t-squared variable. Okay, that's the expression for the Hoteling's t-square. We will not be using it very often, since we would need it to calculate these confidence regions, the joint confidence regions. In general, in practice, we don't do that. In practice, we look at the individual values and sort of start making inferences like that. In practice, this is not what theory says we should do, but in practice, you normally do that instead of doing multivariate tests. In two dimensions, these tests are okay. 3 dimensions, but we'll be dealing in some of the predictive models that we need that we have in practice. We're dealing with 30, 40 predictors, so it wouldn't make sense to look at these joint distributions for that many predictors. Okay. And just like in the univariate case, we can interpret the t-square statistic as the standardized distance between the vector of observed means. Okay, that's a standard. We're standardizing the distance by multiplying by the inverse of the variance covariance matrix. The PDF of t-square, unlike the PDF of the t-distribution, the PDF of the t-square is a PDF that's skewed. This is a skewed PDF, and it has some properties.
I have a question.
Yes.
What do you refer when you say standardized distance?
Because if it was just the distance, just take the distance between 2 vectors, just like that. You standardize it because you multiply by the variance covariance matrix, the inverse of the variance covariance matrix. When you're doing this thing, you're standardizing the distance. Look at the univariate case. This is the univariate case. In the univariate case, you have the distance between y bar and mu null, and the mean under the null hypothesis. That without the s square, that's just the distance. See, if you ignore s square, that's just the distance between y bar and mu null. Now, the way we do it in the univariate case, to see if the y bar is actually too far from mu null to reject the null hypothesis that the mean for y is mu null, we need to say what's a large distance, what's a small distance. That's why we divide by s squared to standardize. So it's this distance is going to be in terms of standard deviations, because the variance will impact how large this distance is, right? If I have a large variance or a small variance, that will have an impact on how large this the distance between y bar and mu is. That's the univariate case. In the multivariate case, the equivalent concept is that we standardize by multiplying the inverse of the variance covariance matrix. Because again, the variance covariance matrix has the information about the variability of each of the variables, each of the p variables, and also the variability of each variable with respect to another one of the variables there, of the p variables. Okay? Is that does that answer your question?
Yes. Thank you,
Good.
teacher.
Okay, Fred. Now, some properties, n has to be greater than p, because if it's not greater than p, then we cannot invert s. So s would be singular. Degrees of freedom are just like in the univariate case, n minus 1 for one sample, and n1 plus n minus n2 minus 2 for two samples. Okay, if we were comparing two samples or just doing inferences for one sample. So it's the same number of degrees of freedom that we have in the univariate case. For the Hoteling's t-square statistic is always used for two-sided alternatives. Okay, it's two-sided alternatives. Remember that the t distribution in the univariate case, we could use it for a one-sided alternative or two-sided. The t-square, the Hoteling t-square, is used only for two-sided alternatives. In the univariate case, we know that the square of a t distribution with n minus 1 degrees of freedom is an f distribution with 1 and n minus 1 degrees of freedom in the univariate case. Okay. Remember when you looked at, for example, regression coefficients, if you look at the square of the t statistic, that will give you the f statistic in the case of a regression analysis. And in the multivariate case, we have a similar result. If nu is the number of degrees of freedom, you subtract p, which is the dimension of the space we're working in, and plus 1, divided by the number of degrees of freedom times p, times the t-square statistic, the Hoteling's t-square, and that will have an f distribution with p and nu minus p plus 1 degrees of freedom. We will not dig into the theory of this thing, but there's some equivalence. There's some things that are very similar when you go to the univariate case to the multivariate case. The univariate, a t-square, is an f. In the multivariate, a t-square, a Hoteling t-square, will also be an f. Okay. Okay. That's about it for the theory in general for the multivariate distributions. Now let's look at the script at AM02 distribuciones multivariadas. If you already have it in your computer, let's run until we implement the package. We install the packages. We're going to use Kern-Smooth to estimate densities, ggplot2 to generate the graphs, and GridExtra to draw multivariate distributions también. Yeah, okay. So run all those lines. Oh, I didn't have any. I've require. Okay.
Which were the scripts that we have to download?
This is AM02 distribuciones multivariadas.
Okay.
Okay. It's and once you're there, since you're already getting to bright space for this thing, download also to your computers this is AM02 distribuciones multivariadas, but also download AM03 análisis de componentes principales. You can download that right away, since you're there. Now, when you download analysis of componentes principales, as you can see here, there are two scripts there that we're going to use. One is called simulación. The other one is called Swiss banknotes. We're going to do the analysis, the principal component analysis of the Swiss bank notes.
So teacher, we don't have to download the simulation, the first one.
Yeah, both. Yeah, download both.
Okay, thank you.
Simulation and Swiss bank notes, both. And the data, I believe you already downloaded the Swiss bank notes data, right? To your laptops.
I don't have it. Where is it, Professor?
These
data.
are the Brightspace scripts, AM03 analysis de componentes principales, which has two scripts, and AM02 distribuciones multivariadas. which is
But the
one.
data of the Swiss bank notes,
Pardon
where
me?
is the data of the Swiss bank notes?
Yes, the data on Swiss bank notes. I thought you already downloaded that, but that's in the section of data sets.
Oh, okay,
Here it is, Swiss bank notes.
thank you.
Okay.
Teacher,
Yeah.
I have two of Swiss bank notes. I download the two of,
Let's see. Let me see what.
I have one that have a space and the other that doesn't.
The first one is a TXT file. Let me take a look at that, and that's separated by tabs. And the second one, left right space. The second one. It's open with this. Oh, it's exactly the same. I don't know why it's duplicated there. It's the same file.
Okay, thank you.
No, you're welcome. In the Swiss bank notes, it's separated by tab. So if you go to line 35 in the script and run all that, I
Wait,
already installed the packages. So I'm going to say SBN with CSV, and I have the Swiss bank notes data loaded already in my space here. So as you can see, well, the Swiss bank notes has this is just the head, those are the first 6 observations, but it's a dimension of 200 by 7 variables. So it's 200 observations with 7 variables. We have 100 Swiss bank notes that are legit, and the others are false. Okay. Now we have the length of the note, the left height, right height, inner to lower, inner to upper, diagonal, and the information whether it's counterfeit or not. Okay, that's the information we have. It's if it's counterfeit or not. Is everybody ready to this point? The script?
Not yet, teacher. Can you wait a second?
You let me know when you're ready.
Yes, thank you. Done, teacher.
Done? Okay. Thank you. The first instruction that I have here is this is just, you don't have to do it. ggplot generally generates the plots with a gray, sort of light gray background, and the title is aligned to the left by default in ggplot. So since I prefer a white background and I want the title in the center, I always run this theme set. Remember, ggplot has the layers, and one of the layers is the theme. And so I set the theme to a black and white theme. The position to the right, when the legend positions to the right, and then the title, the subtitle centered. So I say justified, horizontally justified in 0.5, which is centered, and also the subtitle. That will hold for all the graphs that I generate now. Right, in theme set. Did I install ggplot? Oh, no. ggplot is important. It tells me that I have problems here. Loading version 3.3.3. Let me try it here. When you have problems with the instruction here, you can always try the install packages here. ggplot 2. Okay. Install. I'm going to say yes now because the package that I tried to download here is not working. So I'll say yes. It's going to restart. It's going to restart R.
Teacher, what was the thing that you did first? Did you run the Swiss bank notes or something like
Pardon me? I didn't hear you well. Yeah.
did you run the Swiss bank notes first? Because I don't know why I have an error in the file or something like that. It says it cannot open the connection in file.
Oh, did you change your directory to the directory where you have the file?
Oh, I don't know. I don't think so. Let me check. Thanks.
Okay, so just type get wd and check if that is the directory where you have your data.
Okay, thank you.
Okay. So I installed already the ggplot2. Now I can run this theme set. No. Okay, I hadn't run the library function of ggplot2. Okay, so all I'm doing is setting up ggplot so that the graphs come up in black and white and the titles are centered. That's what I'm doing here, okay? Now let's see how we can plot these univariate estimates of the density function. We'll take the two variables that are in the presentation, okay, which is inner to lower and inner to upper, to estimate the density function. Okay. So here I'm at SVN. If you look at SVN, names SVN, the Swiss bank notes. The fourth is inner to lower, and the fifth is inner to upper. Okay. So I'm setting. I'm doing it like this, but I could do it. I could say SVN, and I want inner to lower. Okay. It's exactly the same thing. I find it easier with the names because I don't have to be counting which column I have the data. So these two instructions are exactly the same. So I'm calling ITOL, the inner to lower the distance, that's inner to L, that's why I put the I in capital and L in capital. I to L is inner to lower, and I inner to upper. I call it I to U. And I'm going to define, if you look at the structure here, structure of SVN, you see that counterfeit appears like an integer. This is in fact a factor. It is a class, okay? It's a factor. So I'm going to define it as a factor here. Now I'm going to calculate the density, we estimate the density function with the function density for the inner to lower. And I'm going to call that F underscore inner to lower. That's it. Density for the inner to lower. If I look at the structure of this thing, it tells me that it's a list of 7 elements. I have X, a grid of X, values of X, Y, which will be the density estimate. Then I have BW, I forgot what it is. We have 200 observations. This is a 0.4. I forgot what this thing is. Doesn't matter. It tells me which function it's called, the data name, and if it has missing values. Okay. And the attribute, it tells me that the class that this object has is a density. It's a density estimate. Okay. Now, when you want to send files, send output to a file, you can use the function sync. If I use sync, I will send to the following instructions, the output of the following instructions will be sent to a file. So I can name the files, and in this case, for example, I'm going to put this information in a file that is called prueba, and I'm using the function paste that we already saw, prueba, and then I add the date, and I end with a .txt. So I'm writing a text file, and I'm setting the name of the file to include the date, today's date, so that if I do this process other times, I will have the file name with the date. So I'll do it here. What's going to happen is that the result of this function cat is going to go to that file. I add a line, \n is a new line, summary, and I'm sending the summary, and I'm going to say sync. So I'll say this thing here. I'll run all these lines. And now if I go to my directory where I have what my working directory is, which was in my case, Análisis multivariado and datos, I'm going to go to that directory. Datos. And now I have a text file. I called it prueba. If you look at here, the name is, let me increase the size. The name of the file is prueba 2021-08-23. So I know that that's the date that I created this file, and the result of summary is sent to this file. Okay, so if I want to send output to a file to use it later, we can use the sync function. Okay. So we now have a summary of these the statistics of the minimum, the first quartile, the median, the mean, the third quartile, and the maximum. Now, I'm gonna stop doing the syncs. Well, I'll do it this one, because if you want to keep appending to a file that we already created, let me close this file. This is not the file. No, that's not it. I already closed it. So what this does, append equal true, will keep adding the results in the console to the same file. So this is useful if you're running something that you want to take later and take information from the console because you already have the console saved in that file. Okay. So I'm going to say sync paste prueba, the same file, sys date, and append equal true, and it will add this thing. I add a new line. I break a line here, and then I say a title quartiles the ETOL, and I print the quantiles. Okay, so I say sync, and if I go to my directory, now I have the same files, the same name, but it added this title quartiles, the inner to lower, and I have the quartiles here. Okay, I have the quartiles here. Now, when you use the summary to get the mean, max, and first and third quartiles, there will be cases where your quartiles here will not coincide exactly. It will be very close in terms of decimal points from the ones you list here, because the algorithm that it uses in the quartiles functions is slightly different to get the quartiles. Okay, so don't be surprised that happens. Now, what X has the grid for which the density function has been estimated. Okay, and the starting value for X is the minimum minus 1.10 times the interquartile range, and the maximum is very close to the maximum ITO plus 1.11 interquartile range. Okay, so I'm going to do the density estimate here. That's the same structure. X has the grid for the values of the variable, and the Y's, the Y is the estimate of the density. Okay, and it starts in 6.95, which is roughly the minimum value for inner to lower minus 1.1 times the interquartile range. That's for default how this function density works. Okay, so I'm going to grab the two charts, one row in two columns, and I'm going to plot the inner to lower and the inner to upper, and I go back to the one chart per panel. Okay?
What does the par function does?
The paremf row, what this function does is tells me the next graphics commands that you're going to see. I want to display my graphs in one row in two columns.
Okay.
Okay. If you wanted two rows, one column, you would say 2,1. Or if you want a grid of 4 charts, you can say 2,2, and that'll give you a grid of 4 charts.
Okay.
That's it. Par is a function for the graphics parameters, not for ggplot, but for the normal plot parameters from R. ggplot is a package that comes apart and has some nice features to produce nice graphs for publication and stuff like that. Okay. So I return it. If you see here, I'm returning to one plot per in each of these panels, just one plot. So I set it up to Z,1,1. Now let's do the same thing using ggplot. Here, in these two graphs, we are ignoring whether the banknote is counterfeit or not. Okay, we're ignoring that. We don't know if it's counterfeit or not. So now we're going to do it with ggplot. With ggplot, the way we do this thing is we're going to use ggplot, and then we say I'm going to store the object in a variable in an object P1. I'm going to store the graph there. I'm not going to display it now. So I say ggplot SVN is my data frame. Then I do the aesthetics. the statics, I'm saying X is equal to inner to lower. That's my data from the data frame, inner to lower. So X is going to be that. And I just said add plus geom density. With that, ggplot knows that this is the values for the variable X. And what I want to plot in the y-axis is the density estimate of these variables, right? For evaluating each of these points. Density estimate is a non-parametric density estimate based on kernel, on a kernel density estimation. I do this P1, I do P2, is the same thing. Now here, the parameter row that we used here to do if I want to use one row, 2 columns, doesn't work with ggplot. Okay, we need the package grid extra. Oops, if we I didn't do the control enter. Control enter. That's my library that I'm going to use, and I'm going to arrange P1, P2 in one row. Oh, gee. Do not find the current read arrange. Library GG media function package. Okay. Let me see it. Let me try again. I'm gonna go back here. I thought I installed and I didn't give me an error to install. When I installed GG Grid Extra, let me check again here. Loading required library Grid Extra. Now it should work. Okay. Here are the two graphs. The inner to lower and the inner to upper. It's similar to the graphs we saw earlier. In some sense, the others and you can see here the others. Now I want to close it. If you want to see in these graphs, it shows that they sort of end the way we expected, right? We expected that to end at 0 here. Okay, that's not happening here in the graph generated by ggplot, but you can fix that by adding values to the left of the smallest observation, doing something like the other command does, which is takes the minimum and subtracts some percentage of the interquartile range to get the minimum data point. So this could fall up to 0. Okay, but that's the density estimate from using ggplot. Now, if we know that we have another variable that tells me if the bills are counterfeit or not. I can incorporate that in the graphs. So what I'm going to do is clean the graphs here, and I'm going to create a P1 graph with SVN. Aesthetics is X equal inner to lower, but color is counterfeit. So I'm going to separate this with this ggplot understands that it's got to separate the densities for the values of color. I only have 2 values for counterfeit, 0 or 1. If I have 3 values, it would use 3 different colors. So I'm going to do the same thing, and I'm going to use geom density again. I do the P2 again, and I grid arrange the plots. And now it shows me the different density estimates for the inner to lower and the inner to upper, which is the ones we saw in the presentation. Okay.
Teacher, I have a problem in there.
And what gives you an error?
Yes, it says warning message. In unit 1, MPC reach elapsed time limit.
Okay, let me. Can you please share your screen?
Yes. From here.
Oh, because that, don't worry about it. It's probably you type that more than once. See here, when you in the first div off, it gives you no device one. The
Yeah.
warnings, it didn't matter. That really doesn't matter. If you do it again, there's no device to turn off because you haven't produced another graph.
Oh, okay.
Okay.
So if I run this, it should be fine.
It should be fine. Yeah.
Okay.
Oh, you stopped it, right?
Yeah. Oh,
I thought you pressed the stop sign there. Oh no, I didn't.
no.
Last time limit.
I think it stopped working.
Yeah. Let's see. Can you make your plotting area a little bit wider? And type down in the console if you want graphics of graphics
Off?
dot graphics dot before the off. There you have it, graphics dot off.
This one?
Off. Yeah, select that one. That's it. Then enter. Something is wrong with it. It's giving you a reached elapsed time limit. I don't know why that is. It's giving you that. Try the plot again, I mean, and see if it works.
Okay. Let me try it and I tell you.
Okay.
Thank you.
You're welcome. Okay, now let's estimate the joint density. To estimate the joint density for two random variables, we use the function bkd2d from the package KernSmooth. Okay. For this package, we're going to use the two variables, 4 and 5, the inner to lower, inner to upper. The syntax of the function says, give me the variables that you want to plot, which bandwidth I'm going to use, and I'm using here a bandwidth equal to 1.06 times the first column, the inner to lower, and the second column which is the inner to upper, times 200 divided raised to the minus 1/5. These constants are sort of empirically the right constants to use for these 200 data. If you had more 200 data points, you would use 300 if you have 300 data points. But again, this is just to illustrate what this looks like. It gives you an error, bandwidth. Did I install? Let me check if it did give me an error when I installed the KernSmooth. Now let's go back here, because that's a function from KernSmooth. Oh, it worked. And I'm going to display the both graphs that you saw in the presentation, where I have the joint density and the product of the marginals. See? Here are the two graphs that we saw. This is a joint, and this is the product of the two marginals. So as we saw that they are not independent. If you look here, what I did, dp is d1y has the density estimate, the marginal density estimate for the first variable, okay? And d2 the signal $y has the estimate, the vector of estimates for the y-axis for the second density. And this thing here is a vector multiplication. Okay, I'm multiplying to multiply vectors. You would use this percent sign star and percent sign, and that gives you vector multiplication. Okay.
Can you repeat what is D1 and D2, please?
Okay, let me go back a little bit here. First,
Thank
you
you.
computed the joint density, right? Now, in D1, I'm setting up the joint density estimates for the inner to lower, which is the fourth variable. And in D2, I'm doing the estimate density, the density estimates for only one variable. DJ has the joint for both 4 and 5. See, DJ has the joint density estimate for two variables, inner to lower, inner to upper. That's when putting the two columns there. Here I'm using a different functions. This function computes a two-dimensional density function. Okay, estimates a two-dimensional density function. And this one here estimates a one-dimensional density function. So I'm estimating the marginals, which are D1 and D2. D1 and D2. But if you look at the structure of D1, I'm going to here structure of D1. It's a list of two. The first element, which is called X, has the X-axis, let's say, for the density estimate. And the second element, Y, has the density estimates. So these are the marginal density estimates for both variables. And I'm multiplying them to see if the marginal density estimates give me the joint density estimate. Okay, so I'm doing this vector multiplication. And I'm graphing, first I'm graphing the DJ. So this is a perspective of D1x and D2x. And what I'm plotting here is DP, which is the product of the two marginal densities. Okay. And then in the second graph, I'm plotting the DJ, the X1. DJ is this frame here that has the joint density estimates. So I'm plotting the joint density estimate for X1, for X2, with a perspective graph, and the estimate, which is F hat. If you look at the structure of DJ, DJ has X1, has X2, which is the second variable, and then it has F hat, the estimate of the density. That's the third object. And I'm using the perspective graph, so it requires three variables, X1, X2, and Y. Okay, or X, Y, Z, whatever you want to call them. And that this one produces the product of the marginals, and second one produces the joint density function. Okay, because that is this too. Okay, is that that help clarify?
Yes, teacher, thank you.
Okay, okay, well. Okay, are we ready?
Yes.
Great. I'm going to share my screen, and we'll start talking about the linear, no, principal component analysis. I'm looking for the presentation. It's AM03. This is the AM03 principal component analysis. Okay. Now, what's the principal component analysis? Principal component analysis is an unsupervised learning method. And what the main objective in PCA is to reduce dimensionality. This was particularly important many years ago when there was no computer power was very limited, and for certain models. Now, in regression analysis, for those of you who took regression analysis, you may have heard the term collinearity or multicollinearity, and that's when several of the independent variables are highly correlated. Well, principal component analysis is a method to reduce number of variables and will contribute to reduce multicollinearity when we have it. So the objective is we have a large number of variables and we want to reduce that to a smaller set of artificial variables, which we call principal components. And the objective is of these fewer artificial variables is to explain as much of the variability that's present in the original variables as possible. Okay, so that we want to all the p variables we have represent certain variability in behavior of the population, and we want to find a subset of those variables, and not really a subset. It's we want to find some artificial variables that we will build based on the original variables that can explain most of the variability present in the original variables. Now, in this case, it's a non-supervised method, so there is no dependent variable here. There is no independent variable. All variables are equal, let's say, and we do not assume that there is a particular grouping of the variables. So just a bunch of variables, if we want to see if we can represent the variability that those variables represent, if we can have that being reduced to a few components called principal components. Okay. Now, the only assumption we make is that the vector of means and the variance covariance matrix exists. Okay, both. We have a vector of means and the variance covariance matrix are both existent. That's the only assumption. We don't make distributional assumptions here. The method consists of finding the different components in a sequence. The first principal component we find will be a linear combination of the variables that has the maximum variance, that represents the maximum variance in the whole set. Okay, so essentially what it does, when we look for that first principal component, we're looking at a dimension along which observations have the largest separation. That will be the first principal component. Once we have that one, then the procedure looks for the second one. The second principal component is the one that, after I've already considered the first one, how much variability is represented by the second principal component. So the second principal component will be a second linear combination with maximum variance in an orthogonal direction to the first component. So we will be building essentially what principal component analysis does. It rotates the axis, the original axis of the p variables, so that with less obvious components, we can represent most of the variability in the data. And the third would be, the third one in order would be the one that has, after the first two, the maximum variance, and it will be orthogonal to the direction of the first two principal components.
Sure, one doubt.
Yeah.
In order to PCA to work, they have to be independent?
No.
No?
They have to be somehow correlated.
Okay, perfect.
There's got to be some certain level of correlation. If I have one variable that has zero correlation with others, then I shouldn't even consider that variable for a principal component analysis.
Okay,
Okay.
thank you.
No, you're welcome. Now let's remember something you learned in linear algebra is eigenvalues and eigenvectors. Let's consider a matrix A, which is a P by P matrix, a square matrix. And if I don't know if you remember, but if there is a number lambda and a vector gamma, such that this equation, the matrix A times gamma equals lambda, the vector times gamma, the vector gamma, then we say that lambda is an eigenvalue and gamma, lambda is an eigenvalue and gamma is an eigenvector. And it can be shown that the lambda, the eigenvalue, is one of the roots of a polynomial expressed by the determinant of A minus lambda times the identity matrix equals 0. So the lambda will be a root of this polynomial. Okay, that's how we define the eigenvalues and the eigenvectors for any square matrix. So first of all, they exist for square matrices. So we're starting with a square matrix A. So if we have P variables, there will be up to P eigenvalues, because this equation, the determinant of A minus lambda times the identity matrix of dimension P, will have P roots. Maybe some of them will be equal, but that's why it says therefore up to P eigenvalues. We may have one or two which are equal roots, right? So if we have P variables, we'll have P eigenvalues. And we'll have P eigenvectors. Okay, for each eigenvalue, there is a corresponding eigenvector. And if we denote by capital lambda the diagonal matrix that has lambda 1 up to lambda p in the diagonal, then the determinant of A and the trace of A can be written as this way. The determinant of A is just the product of the elements of the diagonal, which are the eigenvalues, the lambda 1 up to lambda p. And the trace, just the sum of the diagonal elements, which is just the sum of the eigenvalues, lambda 1 up to lambda sub p. Now, you also studied in linear algebra the spectral decomposition of a matrix, or Jordan decomposition. And that decomposition relates the structure of a matrix with its eigenvalues and eigenvectors. That's what that decomposition does. And what it says is, for every symmetric matrix, A, which is P by P, we can express A, this is the decomposition, that Jordan's decomposition, we can express A as gamma, lambda, gamma transpose. Lambda, capital lambda, will be the matrix that we already saw, the diagonal that has the eigenvalues in the diagonal, and gamma will have the matrix that contains the eigenvectors. So this is the Jordan's decomposition. Any symmetric matrix A can be decomposed in this form. Then the capital lambda will be the diagonal matrix that has the eigenvalues in its diagonal, and gamma will be the matrix that has each of the eigenvectors as a column. Okay, and gamma is an orthogonal matrix. Because remember, when we defined how we obtain the eigenvectors, the second eigenvector is orthogonal to the first. The third eigenvector is orthogonal to the first two. So gamma will be an orthogonal matrix with eigenvectors gamma 1, gamma 2 up to gamma p as their columns. Okay, which are these are the eigenvectors of matrix A. This is Jordan's decomposition. And that brings us to the concept of standardized linear combinations. Again, the objective of PCA is to reduce dimension of the observations. One way to achieve that would not be reasonable at all, would be to retain only one of the variables. Say, if I have p variables, I can reduce dimension by just considering one. Or I could just consider the average of all the variables, okay? The average of the p variables, which would imply that each one has the same weight. And I'm reducing dimension. Instead of looking at the p variables, I look at their average. And I'm reducing dimension. But those are not reasonable ways to reduce dimension. A more reasonable approach would be to use a weighted average, right? Because not all variables contribute to the variance of the whole set equally. So we define a linear transformation, delta transpose times x will be the sum j equal 1 to p of delta j times xj, where xj is the jth original variable. So we have of the original variables j equal 1 through p, x1 is the first original variable, x2 is the second original variable, and so on. And we're calling it standardized because we're forcing the size of the vector delta to be less than or equal to 1. Okay. The modulus of delta has to be less than or equal to 1. That's why we call it the standardized. So that will be we're going to be looking for linear combinations of the original variables in such a way that these coefficients have a modulus equal to 1. Now, the weight vector can be optimized to investigate and detect very specific characteristics. We're going to try to find the delta vector so that we achieve the objective that we have with principal components analysis, and that is to capture most of the variance in the original variables in fewer components. Okay, this is called a standardized linear combination of these original variables. And a particular objective will be to choose delta to maximize the variance of the projection delta transpose x. Delta transpose x, it's nothing but more than a projection of the original variables in some other space. It's just a projection. Okay, we're multiplying the delta transpose times the matrix x of original variables. So what we want is to choose delta to maximize delta transpose x. We impose this condition because I can find arbitrarily large delta that can be maximizing that variance, right? So to bound that and to standardize it, that's why we have the condition that delta in absolute value, the length of delta is 1. Okay, the modulus of delta is 1. We want to maximize the variance of delta transpose x, and that is the maximizing the variance of delta transpose, the variance of x times delta. In a multivariate case, the variance of a vector times a matrix, where x is the matrix of random variables. See here, the random variables are x. X is the matrix of random variables. So delta is not random. Delta is a constant that we're going to be looking for. So the variance of some vector, I'm going to use different notation because that's a general result. So when I compute the variance of a vector transpose times a matrix of random variables, I'm going to use y now. That's always going to be V transpose sigma V, where sigma, this is the variance of y. Okay. In the univariate case, remember, when we multiply one constant times a variable, a random variable, the variance is the constant squared times the variance of a random variable. Well, here's the same thing, but instead of having the constant square, since it's a vector, we take delta transpose, multiply it by, pre-multiply it by the variance, the covariance matrix of X, and post-multiply it by delta. Now, the interesting, to call them some way, the interesting dimensions of delta
Teacher,
are, yes,
in the thing that you wrote, sigma is the variance of J.
sigma will be the variance of Y, yeah.
Thank you.
Yeah, no, you're welcome. The variance covariance matrix of Y. We're assuming here that Y is a matrix, a random matrix, right? That has P random variables, P random vectors. Okay. Now, the directions of delta, after all, we're forcing this condition that delta in the size of delta be bounded by 1 is equal to 1. We're doing that to standardize. Okay, so in essence, what matters is the direction of delta. Every vector represents a direction in one vector in 2 dimensions. The one represents a direction in those 2 dimensions, and in 3 dimensions, it's one vector represents a direction in 3 dimensions. So the interesting directions of delta are found through the spectral decomposition of the variance covariance matrix. So we're starting to use the results from linear algebra that you learned a few semesters ago. Now, it can be shown that the direction delta is given by the first eigenvector gamma 1, which corresponds to the largest eigenvalue delta 1. Okay, so when we maximize that, we can be shown that the delta, the direction of delta, corresponds to the direction of the first eigenvector, and the first eigenvector is the one that corresponds to the largest eigenvalue of the variance covariance matrix, sigma. Okay. Now we'll show 2 projections of a set of data with mean 0. The first one is an arbitrary projection, while the second one is a projection in the direction of the first eigenvector. So we'll take a very simple case. Here is an arbitrary direction. Okay, these are my data. I have 2 variables, x and y, or x1 and x2, and I can pick any delta, any vector, multiply it by it gives me multiplied by sigma, whatever. But the important thing is that the vector gives me a direction. In this case, we chose this direction. This is the vector that goes here from 0 to 0. We call it that's the direction that gives us that vector. That's an arbitrary vector. The vector we're looking for, that corresponds to the first eigenvector, is the one that's gonna take the direction that maximizes the variance in the data. And if you look at this graph, here, the variance in the data that we have here, here we're not capturing that much of the variance, right? With this vector, with this dimension, we're not capturing that much of the variance, because we're capturing, in essence, we're capturing only 26% of the variance in that with that particular vector. The one that we're looking for is the one that maximizes that explained variance. So if you took this data, the vector that would maximize the variance would be this one here. You can imagine selecting several vectors here. Let me do a bunch of graphs here. See, I picked, let me first clear these drawings that I made. And I'm going to use a different color. See, I can different vectors delta give me different directions, right? I can have this one give is that I will extend this thing. You can extend that, or I could have chosen something like this. Let's see, a vector like this, or a vector like this, or a vector like that. And if you project this data to these different vectors, you'll see that none of these explains a lot of the variability. But this one here, this vector that we have here, this one does explain a lot of the variability, because most of the variability is occurring along this direction. So if you look at all the points here, most of the variability is actually occurring along this direction. Here, the variability that occurs along this direction is very, very small. I mean, we have these few points that have a variability in that direction, whereas here, most of the data fall along this direction. So that would be the first eigenvector, okay? That would be the first eigenvector. And the second eigenvector will be orthogonal to that. So the second eigenvector will be something like this, orthogonal to that, okay? That explains the remaining 12% of the variation, okay? So this is the vector we're looking for when we're looking for the first eigenvector, and that corresponds to the largest eigenvalue. Now, the standardized linear combination, SLC, remember, is the standardized linear combination. The standardized linear combination, which contains most of the variance, is obtained then by maximizing this expression. And this will be the principal component number one corresponding to that data that we have for the original data, the X data. Then once we have that principal component one, the second principal component that we're going to find, this is I'm calling it here Y1. It's the first principal component, is gamma 1 transpose, which is the first eigenvalue times X. And that's a transformation of X. See? It's moving X to a different space. The second vector, the second principal component, will correspond to the eigenvalue that has the second, that's the second largest eigenvalue, and that I'm representing here by Y2 is gamma 2 transpose, the eigenvector 2 transpose multiplied by X, which is the second principal component of we call it here PC2 or Y2. So it's transforming. Okay, so in this graph here, this will be this direction is representing the first principal component. And when I drew this thing, what I've done essentially, if I draw the line here that we had, this line, this will be my second. So what we actually did was rotated the axis, right? These were the original axes were these ones here. Let me draw them here. Let's see. The original axes were this, and these are my original axes, right? So in essence, what we're doing is just rotating the original axis. We're rotating them this number of degrees, let's say. Okay, it's a rotation of the axis that we're looking for to explain most of the variance. Now, if we continue this way, if we have p variables, then we'll find the third principal component, the fourth, up to the pth principal component. We'll have as many principal components as original variables. Okay. If we do that thing in p for a general case of p variables, then we can write that down in the following way. We denote x is the original variables, and they have an expected value, a mean of x. Expected value of x is mu, exists. Well, that's one of the assumptions we made. And the variance covariance matrix of x is sigma. Okay, sigma can be decomposed this way with the eigenvectors, the eigenvalues, and the matrix of eigenvectors transposed. So expressing the variance or variance matrix like this, and in x, we can use the notation we introduced for the matrix that contains the eigenvalues, and the matrix that contains the eigenvectors, which is this gamma. We can obtain the principal component transformation by defining y. Remember, I called it here y1, it's the first principal component. It's a transformation that transforms the original variables to a first principal component. Y2 is the second principal component. It's a transformation that transforms my x variables, original x variables, to the second principal component. So I have p principal components, right? I have y1 up to yp. I denote that by the vector y, and those the principal components then will be obtained by gamma transpose times x minus mu. That will give me the projection, the variables x in the new space once I've rotated that thing. So it's just rotating the space in such a way that I can capture most of the variability in the first dimension, then the two largest variability in the second dimension, and so on. That's essentially what we're doing with principal component analysis. Okay. I'm centering here the variables to obtain a principal component transformation y that has zero mean. Okay, just for convenience, we subtract the mean of the original variables and apply the transformation given by the eigenvectors of the variance covariance matrix. Now let's do an example. Let's consider a bivariate normal distribution as variance covariance matrix 1 in the diagonal, and rho, which is the correlation of the diagonal. It's only two variables here, okay? And let's assume that rho, the correlation between x and y, between x1 and x2, is greater than 0. So have greater than 0 correlation. Then from this matrix, we can obtain the eigenvalues. Lambda 1 will be equal to 1 plus rho, and lambda 2 will be equal to 1 minus rho. These will be the eigenvectors, okay? Again, the 1 over square root of 2, what that is doing is only standardizing, okay? That's standardizing. This will be the two eigenvectors, gamma 1 and gamma 2. The principal components transformation, then, as we saw in last slide, will be the matrix of eigenvectors times x minus mu, okay? In this case, I'm assuming that x has a normal distribution with mean 0 and variance covariance matrix sigma, so mu is 0, mu is the vector 0. If we take that transformation, we'll take gamma transpose times x minus mu, and remember, gamma transpose is 1 over square root of 2, 1, 1, and the other vector is 1 over square root of 2, 1 minus 1. Okay, this is the gamma, this is the matrix gamma times x, so that my transformation would be y1 will be x1 plus x2 divided by the square root of 2, and y2 will be x1 minus x2 divided by the square root of 2. Okay. Now, so that you don't get that bored, let's I'll do it very easy. Let's show that lambda 1 is this, is 1 plus rho, and lambda 2 equals to 1 minus rho, and these are the gamma 1 and gamma 2 matrices. So I'm gonna stop sharing, and you're gonna show that in groups, so you have some fun. It's very easy, so I'll give you just 5 minutes in group.
Teacher?
Thank you.
Okay, so let's continue. That's we were here. So those are the eigenvalues and the eigenvectors. Now, the principal component transformation is this one here. So when the principal component will be equal to y1, y1, which is the principal component, will be equal to 1 over square root of 2 of x1 plus x2, and y2, 1 over square root of 2, x1 minus x2. And that gives that translates everything to a new set of axes, where the first axis is the first vector, the first eigenvector, and second axis is this one. Now let's verify, let's compute the variances for the first and second principal components. If you look, the variance of the first component is 1 over the variance of this thing, 1 over square root of 2, x1 plus x2. That is that's 1/2, because that's the square goes out of the variance. It's a constant, times the variance of x1 plus x2. And we know that the variance of x1 plus x2 is the variance of x1 plus the variance of x2 plus 2 times the covariance of x1 and x2. And since we know the variance covariance matrix, we know that's equal to 1/2, 1 plus 1 plus 2 rho, and that'll give you lambda, that 1 plus rho is the first eigenvalue, right? It's the first eigenvalue. But notice that it is 1 plus rho, okay? And the second one gives you 1 minus rho. But remember, here we said that rho is positive. Okay, rho is positive. So since rho is positive, the first eigenvalue is larger than the second one. So we see the first eigenvalue is the largest one, and then the second one is smaller, because that's 1 minus rho and this is 1 plus rho. That's why the eigenvalue. Now, another thing that we'll see later is that the eigenvalue, an eigenvalue that is greater than 1, represents, what that means, if our eigenvalue is greater than 1, it means that the corresponding eigenvector with this eigenvalue is explaining more than a single variable of the original variables. If it is less than 1, which will be this case, see, in this case, the eigenvalue will be less than 1, in this case here. So what that means is that the corresponding eigenvector is representing, is explaining less than the variance that's explained by any one of the individual original variables. Okay, so we'll see later that that's one of the possible criteria to select how many eigenvalues, how many eigenvectors should we consider. Now let's generalize this thing. We have a random vector x, which has a multivariate normal distribution. But it doesn't have to be normal. Okay, the usual assumption is normal. They don't have to be normal. With mean mu, the only thing that we require is the mean vector exists and the variance covariance matrix also exists. And let Y the principal component transformation be with principal component transformation. So it's a gamma transpose, which is the matrix of eigenvectors times X minus mu. Okay. Now, the expected value of Yj is equal to 0 because we remember that in the transformation we're subtracting the mean. Okay. So the expected value is 0. And the variance of Yi of the jth transformed variable, the variance is lambda sub j. The covariance between Yi and Yj, that is the covariance between any pair of the transformed variables, is equal to 0. Why is it equal to 0? Because if you can compute the covariance between Yi and Yj, you get that that's gamma I transpose times the variance of X minus mu times gamma sub j. And that's gamma I transpose times variance of X times gamma sub j. Okay. For ID, if I is different from j, this covariance is going to be 0 because the variance, we can express the variance of X as gamma lambda gamma transpose, and gamma transpose gamma, we remember that gamma is an orthogonal matrix, so gamma transpose gamma is the identity. So now I replace this variance of X there in that equation, above equation, and what we get is that gamma I transpose variance of X times gamma j is this one here, is gamma I transpose gamma lambda gamma transpose gamma sub j, and that is equal to 0 if I is different from j, and is equal to lambda sub j if I equals to j, because this matrix is diagonal and the only values that are non-zero are the elements in the diagonal, which are the eigenvalues. Okay, so if I different from j, we're working outside the diagonal of this matrix, then those covariances are 0. So when we do the transformation, the principal component transformation, the transformed variables have covariance 0. That's why this is one of the techniques that is used when we do a linear regression, for example, and we have multicollinearity, because the transformed variables will not have that problem of multicollinearity. Okay. The other characteristic here is that the variance of Y1, the first eigenvalue, the principal component, is greater than or equal to the variance of the second principal component, and so on up to the pth principal component. They go decreasing because that's the way we compute the eigenvalues in the eigenvectors. The variance, the sum of the variances is just the sum of the elements of the diagonal of sigma, the trace, and the product of the variances is the determinant of sigma. Okay, so once we have that principal component transformation, there's some nice properties. In particular, the nicest property is that we have this covariance equal to 0 when I is different from j. For different principal components, their covariance is going to be equal to 0. And the other thing is, of course, it's very easy to obtain the variance and very easy to obtain the determinant of the variance covariance matrix. Now, the principal component transformation depends on what? Depends on this matrix, on sigma. And that matrix is highly influenced by the units of measurement that we have. So when we do principal component analysis, it's very important to standardize the variables. If all the variables that we have are roughly in the same range of values, okay, the units of measurement are relatively similar, then it's not strictly necessary that we do that. But if we have, for example, one variable may be measured in the millions, another variable may be measured in the tens, and that's a huge difference that affect the variance covariance matrix. So what we do is first standardize the variables and then do the principal component analysis so that the dimensions, the units of measure do not impact. Okay, is that clear why we need to do this standardization of the variables, subtract the mean and divide by the standard deviation? Do that to eliminate the effect of different units of measure for the different variables.
Yes, teacher, everything clear.
Okay, great. Well, in summary, algebraically, what principal components are is simple linear combinations of the original p variables. That's it. Geometrically, what these linear combinations represent is the selection of a new coordinate system through the rotation of the original coordinate system, so that the first variable in this new coordinate system captures most of the variability in the data. The second dimension captures the second to last to largest variability in the data, and so on. The new axes represent the direction with maximum variability, and they provide a parsimonious representation of the variance covariance structure. Because if we can represent, if we have, let's say that we have two principal components that explains 85% of the variance in the whole set of data, we may just be content with working only with those two principal components because they are capturing most of what's happening in the data. Okay. So we already said this thing, the principal components depend on the variance covariance matrix. This is an important thing to remember. An eigenvector is such that the direction doesn't change when we apply a linear transformation. So that's a nice property of the eigenvectors. We can apply linear transformations to the transformed variables, and that doesn't change the direction of this eigenvector. So we keep working on this rotated axis. This is a graph. In 2 dimensions, it's very easy to see. For example, here I have 2 dimensions. These are the original variables, y1, y2, okay? These are the original variables. Now, the transformed variables will depend on the eigenvectors and eigenvalues, but the eigenvectors are the ones who set the direction. And as you can see in this set of data, most of the variability occurs in this direction. Okay, so Z1 will be the first principal component, C2 will be the second principal component. Okay, so we're essentially rotating our axis instead of their axis that our axis be this one's original, this original axis. This is the original axis here. And we're rotating those axes. So that now the first axis, Z1, captures most of the variability in the data, and C2 captures the second to largest variability in the data. Okay. So essentially, it's a projection of the p-dimensional data, in this case, the 2-dimensional data, into a plane that shows the greatest separation among the observations. That's what we're doing. In this direction, we have the largest separation among the observations. It's larger in this direction than in this direction. And as you can see here, suppose I have very limited resources, I only have to work with one variable. Well, if I only had to work with one variable, I would choose this transform C1 variable, because that really is showing contains most of the variability that we have in the original data set. Okay. So that's a principle, the concept in this principal component stuff. Let me put the annotate figure here and erase all drawing. Okay. Now, in practice, we don't know the mean, mu, nor the variance covariance matrix, but we use the sample mean and the sample variance covariance matrix. Although we're going to be working with sample statistics here, we'll keep the notation for the eigenvalues of the eigenvectors. So we'll be calling gamma 1 the first eigenvalue of S, okay? I'm using notation because I should use a different letter here because that refers to the population, to the sigma. This is the eigenvalue of sigma, but we'll use the same notation. Gamma 1 is the first eigenvalue of the variance covariance matrix, the sample variance covariance matrix. And the first principal component is given by this expression, is x, my vector x, original data, minus a vector of ones times the transpose of the mean of x, of the mean. Remember that we were taking, for the transformation, we took x minus mu, right? Well, we're doing the same thing, but instead of mu, we're using the sample mean, okay? So this is x minus 1, a vector of ones times x transpose times y1. And that will be the first principal component. And the second principal component will be defined exactly the same, but it will be orthogonal to the first one and so on. So if we denote by keep using the gamma, lambda, gamma, capital gamma as notation for the vector, the matrix of eigenvectors and the matrix of that has the eigenvalues in the diagonal, then if this is the spectral decomposition of the variance covariance matrix, the sample variance covariance matrix, the principal components are given by this vector, which is x minus 1 transpose, or x minus 1 times x transpose gamma, okay? Now, we'll introduce another matrix here just to simplify notation. If we denote by H, the matrix that centers the data, that is the matrix such that when I consider that you see the matrix is the identity matrix minus a matrix that has 1 transpose 1. So what we're doing when we apply H to a vector, we're centering that vector, okay? H times 1, this vector, H times this, H is the vector of ones and the matrix of the vector of transpose of the sample means. When I apply H to that I get 0 because I'm subtracting the mean. That's why we call it a centering matrix. The H matrix is a centering matrix. Well, if we use that notation, then we can write. I'm sorry about this thing, right? No, this cannot. I have to correct this thing now. I can write that variance covariance matrix in this form, which is I'm using this centering matrix here in the middle. So x minus this transpose times H times x minus this times gamma. I have gamma transpose here. And that is exactly gamma transpose times S gamma. And that's equal to the diagonal matrix that has the eigenvalues. Okay. So it's just it simplifies notation and we achieve different results, but simplify the way we express now these matrices. Now we have our lambda matrix that has the eigenvalues is equal to this gamma transpose S gamma. Okay.
Gamma, what was gamma again?
Gamma, capital gamma is the matrix that has the eigenvalues in its columns.
Okay.
Eigenvectors, the eigenvectors. And capital lambda is the matrix that has, is a diagonal matrix with the eigenvalues in the diagonal.
Okay.
Okay. Then the variance of yi, the variance of the yi when I is the ith principal component is lambda I. So the variance of the ith principal component is the ith eigenvector, the eigenvalue.
Profesor, yo tengo, se lo puedo decir en español, perdón, es que
Sure.
I knew that property, the gamma transpose is gamma equals para la diagonal, but I knew it as gamma inverse, not transpose. I don't know if it's the same, because when I saw that theorem for the diagonal, it was inverse, not transpose the gamma, the first gamma, but I don't know.
Well, remember that gamma is orthogonal. So when you multiply gamma by its transpose, you get the identity. So you can put it as an inverse there.
Okay. Thanks.
Because it's an orthogonal matrix. Okay, so gamma transpose gamma is equal to the identity. That's why maybe that's why you saw it as an inverse. Because if it's orthogonal, that'll be the same, right?
Okay, thanks.
Okay. So the important thing here is that the variance of the ith principal component is lambda I, is the ith eigenvalue. And we can express the proportion of total variance in the sample explained by the kth principal component. If I just take each of these lambdas represent the variance of the transformed variables. So if I take the variance of the kth principal component divided by total variance, that's the proportional variance in the sample explained by the kth principal component. So that's a proportion of the variance, of the total variance that is explained by the kth principal component. And that's for k equals 1, 2, and so on. No? So of course, for lambda 1, when I take lambda 1, that will be the largest proportion. Lambda 2 will be the second to largest. Lambda 3 will be the third to largest, and so on. Okay. So lambda 1 will be lambda 1 will be greater than or equal lambda 2, greater than or equal lambda k, greater than or equal up to lambda sub p. We have as many eigenvalues as original variables. Now, basic assumptions that we need to apply principal component analysis. We need to have several variables that are measured on a continuous scale. There are exceptions where you use principal component analysis, and one exception is when with things like a Likert scale. I don't know if you're familiar with the Likert scale, but that's a scale that's used very often by psychologists and social scientists. And they have a question, then you have normally it's about 7 different answers, and they are ordered. So it's from I completely dislike this thing, and then that would be the 1, and then 2 would be I dislike it, 3, and so on up to 7, which is I'm absolutely delighted with this thing. Okay, that's the type of scale. Likert scale can be in 7. They also use 5, and some psychologists use 4. If it's only 4 or 5, I don't think it's the right thing to do principal component analysis. They still do it, but I don't think it's the right thing to do. But definitely with seven different numbers in the scale, that's okay to use principal component analysis. There must be some linear relationship between the variables. If what I mentioned earlier, if I have one variable that has zero covariance with any of the other variables in my original set, that variable is, I can eliminate that from the principal component analysis because it's not related at all with the others. And what these principal components are linear combinations of the rest of the variables, right? Now, how do we determine this thing? If we have a large number of variables, it will be impractical to analyze every pair of scatter plots to see if there are correlations, okay? We'll see now a graphical way to do that for a large number of variables. If we have nonlinear relationships, that we can deal that with transformations. So we may transform and have a linear relationship. The other assumption is that there should be outliers, okay? No extreme outliers, because what happens is that an outlier distorts the information in the variance covariance matrix. Okay?
And the direction, no?
Yeah, it can influence it can directly influence the direction of one of the components.
Yeah,
we have an outlier. So the recommendation here is, if we know that an outlier is justified and there's a reasonable cause for that outlier, we need to take that into account. But otherwise, it's not valid just to eliminate an outlier. It is not valid to do that. Okay. There are ways to impute values for an outlier. If, for example, let's say that we have an outlier because a machine broke down and we don't have measurements associated with that observation. If that was the case, then what we can do is we could use a method to impute the value or the values for the p variables. One method that's usually that tends to be common to impute values is the method based on the nearest neighbors. So let's take, for example, the k nearest neighbors and so on. But in general, we don't really need to do that. Okay. The fourth assumption is we need to have a large sample size to produce reliable results. This is a rule of thumb. It's an empirical result. A minimum of 150 cases and at least 10 cases for each of the p variables. Okay. With very few data points, it would make sense to do principal component analysis. What are the main applications? We said remove support variables that are not adding value. For example, if I have two variables that are highly correlated, I can eliminate one of them, right? For example. Or if I have a variable that's not adding any, let's say I'm studying a bunch of variables and these are demographic variables, and then I have a variable that that has to do with, for example, with the let's say the political environment in the country. That may not be adding because there's no relation at all with the other variables. Reduce redundancy in a set of variables and eliminate multiple linearity. Those are the principal uses of principal component analysis. Now, one of the assumptions of PCA is that there must be some linear relationship among the variables. Okay, let's say I didn't give you a break. Let's just stop here. I'll give you your 20 minutes before the next class.